Hey, thank you, Dr. Weiss. So, welcome to my lightning talk. I'm going to try to get us back on time. I'm Graham Haug. I'm a postdoc in Dr. Robert Paton's group, and I'd love to talk to you today about an ongoing project that I've been working on for a while with two members of the DCN and their research groups. The first, Dr. Dalia Biswas from Whitman College in Walla Walla, Washington, one of the best named towns in the country as far as I'm concerned, and a fantastic undergrad researcher, Benjamin Davis. And additionally, we're supported with some synthetic workflows and insights from the group of Dr. Jessica Kisunzu at Colorado College. So I'd like to thank both of these groups for their fantastic collaborative work with me, and it's just been a pleasure working with them in general. So with that, let's go on to our talk. So first, let's talk about the importance of arynes in the context of synthetic chemistry. So on the left here, we can see, okay, we can generate these benzyne moieties from a variety of different means. And in a synthetic context, this is great because this affords us, maybe in a complex synthesis, the potential to pick a method that's tolerable of all of our other processes that led up to this point, or functional groups, and access these versatile reactive intermediates. Once you can form those reactive intermediates, benzynes are also kind of uniquely positioned to have a lot of means for unraveling this chemical potential energy we've made in this triple bond. This versatility, of course, comes at the expense of energetic input needed to generate these highly strained cyclic sp hybridized carbons. So that's kind of the essential drawback of using this method. Now, wouldn't it be nice if we could find all of the thermally accessible heteroines? Well, yeah, it would be great. So in this project, what our goals are is we want to just in general curate every possible heteroine of any chemical interest whatsoever. And our metric for determining of whether or not we should invest more time of these is their thermal accessibility. And we'll get more into that at the end of this. So just as a first and foremost means of work here, what we want to do is we want to curate a computational set. And in our case, we chose to derive arynes from their parent arynes via dehydrogenation reaction. We want to generate a very easy to use, transparent, robust, and modular computational workflow that allows us to generate, not just for this project, but for any project, a very self-consistent data set with a lot of checks, valid structures, and corresponding molecular descriptors. From that, we intend to derive some statistical models and try to do some predictive chemistry around maybe nucleophilic regioselectivity. And then also we want to try to just, from this vast amount of data that we're collecting about this kind of unique, maybe understudied class of molecules, we want to try to enhance the synthetic and methodological understanding that can facilitate their use in coming years. So talking first to the first 2 points, our immediate goal is just to generate a modular workflow. And part of this project that's unique is that from our group and the Paton group, we work on a lot of workflows and methodological development and DFT studies. We want to expand that understanding and help and grow with other members of CCAS, specifically with the Data Chemists Network. So one of the very hard-written rules in this project is we want to be able to take essentially anyone, be it synthetic chemist, undergrad student, anything, provide them with some kind of templates that can enable them to easily access these kind of studies or use this as a building block for their own internal studies. So with that in mind, our approach to this was to make a series of modules that are very well commented and very robust, transparent, that can lead somebody through almost in an educational way of how to do this chemistry. So we've devised this kind of process that's end-to-end where we can just source SMILES data as long as there's a valid SMILES and it contains some sort of aryne and some sort of internal triple bond. We want that. So we can just grab a bunch of CSVs, check them for relevant data, and compile and deduplicate. From there, we do some kind of pre-processing of the arynes to make sure that we're capable of just arynizing only the valid ones that we want. We use reaction smarts to enable that transformation. And then from there, we start to scale up. And we prepare DFT level inputs for all of those. We use free off-the-shelf software and Orca in conjunction with some of our software from the Paton group. We run these DFT calculations at scale serially on Access supercomputers. using a kind of in-house written script called Porca to run all of these Orca calculations and process them downstream. And then finally, we extract DFT level parameters and calculate this energy of dehydrogenation. So this all kind of works serially. I think the advantage of that is like, yes, there's more involvement, but from that standpoint, it's a kind of an opportunity and an intentional design choice to make people be able to learn these things and then branch off in their own Jupyter notebooks from there. So the result of that is we end up calculating like a CSV of all of these or parent arynes and their corresponding child arynes where possible. We calculate DFT level energies for those and then calculate the energy of dehydrogenation in order to form this. The reason we're interested in this is because you can imagine that a lower energy of dehydrogenation means that there's less energy required to generate this aryne. So that kind of is a proxy for the stability of the aryne that you generate. We've done this for about 76,000 or 7,600 of these Aryne pairs. And from that, we end up calculating this kind of histogram here where we're plotting the dehydrogenation energy against the number of heterodynes. And you can see that according to these kind of somewhat arbitrary thresholds that we've set, anything below about 115 kcal per mole, we consider to be kind of chemical interest. And the vast majority of our data kind of sits in this range. Past about 130 kcal per mole, we consider those to be more or less energy inaccessible. Thankfully, we kind of tail off in that region. And then we have this kind of middle region, which is very interesting, where they may or may not be thermally accessible. There may be some structural features that may be contributing to a higher energy, but maybe if we can understand more about that region, we can kind of give some guiding advice about where to go next with your selection or design with your chemistry using arynes. So one hypothesis that we had from this, which came from a paper from my boss back in 2012, is that the energy of this dehydrogenation, whether it be free energy, electronic energy, may be tied with the ability of these carbons involved in the aryne formation to be more or less sp hybridized. In an ideal world, they could achieve this angle of 180 degrees. Here, obviously, they're in a ring. They can't achieve that, right? So one theory that we had about that was specifically that potentially a nucleophile, right, would prefer to add at this carbon that's more linear.
20 people at the beginning.
Sorry. So we had this hypothesis, and we have this large data set of about 7,000 arynes now. So just as a curiosity and starting point, the first thing that we did is we looked at the maximum internal angle of this. So we wanted to see if there was any kind of correlation between the energy of dehydrogenation and the maximum internal angle, thinking that, okay, the greater that angle that we could form, the closer it is to 180 degrees, maybe the energy would be lower for that, right, from a strain standpoint. So we plotted that, and we're just taking the larger angle between these two of them and then plotting against the energy. And what we can see initially is not maybe a very satisfactory result. You can see this is colored by kind of occurrence, and there are a lot of clusters in these data and some notable outliers. So as a first pass now, my thinking is, okay, we need to kind of think maybe these clusters are a function of the atom that's neighboring to this aryne, and we're starting to drill down using our other descriptors that we've calculated into thinking, okay, specifically how are the kind of substructure relationships maybe responsible for this energy of dehydrogenation. So we still have some work to do from that standpoint. And in the context of this, we have some ongoing projects in our group that maybe have indicated that some of these arynes, as maybe represented by a lot of these kind of corresponding competing representations of arynes here, maybe these arynes exhibit some sort of multi-reference character. Maybe where some of them prefer to sit in a triplet state, some of them prefer to be in a singlet diradical state, or as a traditional aryne. So we're starting to think about this as well and doing some maybe substructure specific DFT calculations to kind of add some more insight to this, because I think there's a large area where we can add in this region, maybe as a function of number of heteroatoms or as a substituent effect as well. So it's kind of an exciting time. We're in the fun phase of this project where we get to do all the data science parts. So expect to see some big jumps from us in the near future, and I'm happy to take any questions. Thanks.